Hi folks, I'm going to spend some time here going through the bootstrapped prediction.r script, which you can find on the course website. And this will walk you through the process of constructing a bootstrap prediction interval or a set of bootstrap prediction intervals corresponding to different values of the predictor in R. And this will be in the context of the newspapers.csv dataset, which I've already loaded into R, and you should do so by downloading and clicking the Import Dataset button as usual. I also want to point out one thing here. If you have an earlier version of this script that you downloaded from the website, you might want to download a clean version because I made a few changes and just corrected a few things that were potentially confusing from earlier. So I'm working with the up-to-date version that you can find on the website right now. Just to remind you of what's in this data set, let's plot it and fit a straight line. So we've got every dot here representing a major metropolitan newspaper. Here's the daily circulation in thousands of papers, so 600,000, 800,000, etc. And here's the paper's Sunday circulation, so Monday to Friday versus Sunday here. And the goal is, given a particular value of the daily circulation, build a model that's capable of giving you a prediction interval for the Sunday circulation, incorporating both parameter uncertainty and residual uncertainty. So let's give an example of this. So I'm going to call x star here as a data frame for new variables, new daily circulations that I want to predict. So if I source this line and ask what's x star right here, just copying and pasting that to the console, you can say I've got a really simple data frame. It's just got one row, one newspaper, one variable, that's daily, with 1,000 newspapers daily circulation. So this is going to be my input, and that's where I want to generate a prediction interval right here on the x-axis and figure out what the corresponding boundaries of that prediction interval are on the y-axis. So the key idea behind generating bootstrap prediction intervals is to simulate future data points. And future data points incorporate two sources of uncertainty. There's the uncertainty due to the future residual, so the part of the forces that affect the data that you've never even modeled in your data set. And then there is the parameter uncertainty, uncertainty about, say, the slope and the intercept of a regression line that should percolate forward to uncertainty about the forecast of a future observable quantity, like the Sunday circulation here. So let's follow the steps given in the course packet and discussed in class for computing a bootstrap prediction interval. So this is a process that we're going to repeat 10,000 times, so we're going to simulate 10,000 notional future data points of Sunday circulation here, all corresponding to newspaper with a daily circulation of 1,000. Let's build this from the inside out and go kind of one step at a time through the interior bits between the braces of this do loop right here. So step 1A here is to fit a regression model to a bootstrapped sample. So I'm doing that in one line here. I'm taking a bootstrap sample of my newspaper's data frame, and to that bootstrap sample, I'm fitting a linear model for Sunday circulation versus daily circulation. Okay, so I'm not going to get exactly the same line that I get for my original sample because I'm going to have some ties and omissions, and that's going to simulate parameter uncertainty right there. And then step 1B is I use that model I fit, and I've stored that model in this object called lm sub. I'm going to use that to predict a new value of y at the corresponding values of x that I care about. And here, those values of x are stored in this data frame x star that I defined up here. So if I execute that command and I ask what's y hat, well, for this particular bootstrap sample, my plug-in prediction is 1334. And just to emphasize that this changes from one bootstrap sample to the next, let's do it again. A different bootstrap sample, a different plug-in prediction, and instead of 1334, what do we get? We get 1407. So these steps 1A and 1B together are what's baking in parameter uncertainty into the future observable quantity here, the future observations that we're simulating, and it's injected via bootstrapping. All right, so step 2, I didn't label it as step 2 here, but line 26 here, step 2. We form a future residual, and the way we do that is by sampling with replacement from the set of residuals of this bootstrap model up here. Okay, so I've got some residuals from this linear model. I'm going to take a sample of size 1 with replacement, and this bit doesn't matter if I'm taking only one sample, but it's good for just to be very specific for what comes next. So here are my residuals. Well, there's only one of them. In this particular case, my residual was negative, minus 56. Okay, and then step 3, I form the future observation by adding the systematic part and the residual part. Okay, so here my future observation is simulated to be 1350. which is about right here on the y-axis. Let's do that whole process again. So a different bootstrap sample right there, a different prediction right here, a different residual right there, and therefore a different observable right there. And what do we get instead of 1350? We got 1436. So if we let this run, and I'm going to do 10,000 bootstrap samples here, and just wait for this Monte Carlo simulation to finish, every time we pass through this do loop, we're aggregating a different simulated future observation. And at the end, we're going to be left with a histogram, and we can summarize that histogram in any of the ways we've learned to do so far, be that compute a standard deviation or compute a coverage interval. All right, so that took a few seconds, but now my bootstrap samples of size 10,000 are done. And let's look at the first few lines of this object bootpred that I've created. So you notice I've got the first 6 rows here, and there's this not very informative variable name called x1 here. That just corresponds to the first value of x that I was trying to predict at, and that happened to be 1,000. Could have been anything that I plugged in there. All right, let's make a histogram. This is the first 6 numbers, but we've got 10,000 of them. Let's make a histogram, and here we go. I would call this a likely distribution of Sunday circulation for a newspaper with a daily circulation of 1,000. That was the X star I plugged in. And if we wanted to summarize this histogram right here, we could compute a standard deviation and say my standard error of prediction is about 115. Or I could compute an interval. And we call this a bootstrap prediction interval. And we use this, we calculate it using the confident function on this first column, the only column of this bootpred data frame. So here the quantiles, the 2.5 and 97.5 quantiles of this correspond to 1123, about right there, and 1573, about right there. And so we could call this a 95% prediction interval generated via bootstrapping. Okay, so that's for one data point corresponding to an X star at 1,000. Let's now repeat that process for many future data points at once. So in particular, let's say instead of a single prediction interval for a newspaper with a daily circulation of 1,000, I wanted to compute the prediction interval for a whole range of newspapers having many, many different kinds of daily circulations. So what I'll do here is I'll generate a sequence of notional daily circulations. These will run from 130,000 all the way up to 1.21 million, and they'll go up in increments of 10. So I'm going to take this sequence right here, constructed using the seek command, and store it as the daily variable inside a data frame right here. So now X star, I've overwritten what I used to have, and if I look at the first 6 lines of X star using the head function, now I've got a newspaper with a daily circulation of 130,000, 140,000, 150,000, etc., all the way on up to, what did we have at the end? 1.16 million, 1.17 million, and so forth. All right. So I'm going to show you how we can modify the previous set of code here to generate bootstrap prediction intervals for all of these newspapers at once, having all of these different possible values in daily circulation. And it's going to involve only a few simple modifications to what we were doing before. Okay? So again, let's go inside out, starting inside the braces here of the do loop, and go through it once. Just as before, we fit a model to a bootstrap sample, so this looks identical to the previous loop here. And for this particular case, we got an intercept of -47 and a slope of 1.41. Now I'm going to make predictions for X star, except X star is a whole data frame with 109 rows instead of just one. And I actually stored the number of rows up here on line 51, the number of rows of X star, in this variable called m. Okay, and so I know it's 101 because if I type m and enter down here, I get or 109 rather. Because if I type m and enter, I get 109. Okay, so this prediction right here that I'm executing on line 63 is for all those values of X star at once. All right, and so now y hat is a vector, and to show you that, here it is. Right, so this is the one for the first X star, the second X star, the 50th X star, all the way up to the 109th X star. And those correspond to the different possible values of daily circulation that I defined in this sequence up here. All right, so that's steps 1A and 1B. Let's take step 2 now, which is to resample residuals from this bootstrap model. Now we've got m different data points where I want to generate a prediction. That was the number of rows of X star up here. M happens to be 109. And so I need to take 109 residuals in order to correspond to 109 predictions for those different values of x star. And so on line 67 here, I'm not just sampling one residual, I'm sampling m of them, little lowercase m here, and I'm sampling them with replacement from this set of residuals of the bootstrap model right here. Okay, so y hat has 109 entries. This vector eps has 109 entries, and I'm just going to add those two together element-wise. So the first element of y hat goes with the first element of eps, the second element of y hat goes with the second element of eps, and so forth. And what do I get now is a vector y star having 109 entries in it, every entry here corresponding to the particular entry in x star. So this would be the 81st value of x star, the 82nd value corresponding to the 101st value, and so forth. Okay, and so if I do this again, whole process, fit a model to a bootstrap sample, use that bootstrap sample to form a plug-in prediction for all of my values of x star at once, sample as many values of a residual as I need to fill in and correspond to all of these different values of y hat that I'm generating, and then finally sum those two, y hat plus eps, we get a different set of simulated data points. So every single entry here is one simulated data point corresponding to a different value of x star. And as before, we'll let the do loop run here. Okay. And at the end, we're going to end up with something a little bit more complicated than before. Previously, when we were trying to generate predictions at only a single point, x star equals 1,000, we ended up with a set of 10,000 numbers corresponding to 10,000 simulated Sunday circulations, which I could then use to form prediction intervals and calculate predictive standard errors. This time we have something a lot more complicated. If I ask for the first few lines of boot pred, now we've got, yes, the first 6 rows, but there's now 109 columns. So let's scroll back to the beginning here, just so you can interpret what you're looking at. This first column corresponds to the first 6 simulated Sunday circulations for the first value of daily circulation that I placed in x star. Okay, and so just to be specific, what was that first value? If I go back here and say, what were the first 6 values of x star? That first value was a daily circulation of 130. So again, going back to the top of boot pred here, those are the first 6 simulated Sunday circulations for that newspaper with the daily circulation of 130,000. Here are the first 6 for the newspaper with the daily circulation of 140,000, for 150,000, 160,000, and so forth. Okay, so the rows here are telling you different bootstrap samples, and there's 10,000 of them. The columns here are telling you the different values of x star that you were trying to make predictions at, and because there are 109 of those, there are 109 columns in this object. Okay, and so this is now a lot more complicated to work with. We're going to need to somehow summarize something about every single column, all 109 of them. Okay. So first things first, let me just form my plug-in prediction right here. Okay, and this is the old way, so this is my best guess. And now let's do predictive standard errors. So calculate the standard deviation. So if I look at y hat now, this is my plug-in prediction using not the bootstrap linear model, but the actual linear model that I fit to my real sample. And now I'm taking this boot pred thing that I calculated using this loop up here. And this line is a little bit terse. It's a little bit hard to understand at first glance, but what is it doing? This is just calculating the standard deviation of every column in that boot pred data frame right there. Okay, so the way to read this here, YSC is going to be my predictive standard error, so my standard error of prediction for Y. This says apply, okay, so apply a function to every column of this data frame right here, and Y column, because that's 2. If we were to say, put a 1 there, it would say apply something to every row, but now we put a 2, so it's apply something to every column. And what are we applying? It's the standard deviation function. Okay, so this says apply to the boot pred data frames, every column, the standard deviation function. So if I execute that, I should have 109 different standard deviations right here, and sure enough I do, and these correspond to the standard deviations of every column of this boot pred data frame right here. Okay, so we're going to come back to line 83 here in a second, and then all the way through at line 89. Right now I just want to skip all the way down to line 96 and 97 so you can compare what these YSEs look like. So these are the ones that we calculated, the standard errors of prediction up here on line 80. Let's compare those, and here they are as a function of the x star that I'm trying to make predictions. So think about this as the prediction standard error as a function of x. And let's compare that to the ordinary standard deviation of the residuals that we were using in naive prediction intervals. So my bootstrap standard errors of prediction are actually lower here than the naive prediction interval, but they're higher out here. And they have this characteristic bowing out quality, that as you go further and further away from the mean, which is somewhere down here around 400, the predictive standard errors get a lot wider and your prediction intervals get a lot wider to account for the effect of additional parameter uncertainty. Okay? Now we can also calculate 95% prediction intervals for every point. That was our predictive standard error. Let's now do the same logic. So up here we were applying to every column, we were applying the standard deviation. Now let's to every column, let's apply the function quantile. And quantile needs a couple of auxiliary flags here. We need to say which probabilities we want to generate quantiles for. So the way to read line 83 here is to say, apply to the bootpred data frame, every column, the quantile function. And which quantiles? Well, we want them to be the 2.5 and 97.5th percentiles, expressed as fractions right there. So if we execute line 83, what we're going to get is actually two numbers for every possible value of x star. And they correspond to the 2.5 and 97.5th percentiles of those histograms. Okay, so here this would be our prediction interval. This goes below 0, so that's obviously something that leaves something to be desired there, because you can't have negative circulation. So let's focus on one out here. This is the 39th value of x star, and this would be the 2.5 and 97.5th prediction interval endpoints of your 95% prediction interval for the 39th value of x star. Okay. Now this is a little bit awkward this is a matrix, right, where the rows of the matrix are the percentiles and the columns are the different values of x. If we wanted to view the bounds themselves as the columns rather than the rows, it displays a little bit more nicely on the screen here. We can take the transpose of this matrix right here, and we do that using this function called t, and that just says take this matrix and flip it on its side so that the rows become columns, and you'll see that if I execute line 89 right here. So now I've got the rows are the different values of x star, and the columns are the 2.5 and 97.5th percentiles of my histograms. And if I want to stack those next to the corresponding values of x star, I can use the cbind function, which says bind these two columns together. So the columns in x star and the columns in this matrix up here. And so what do you get out of here if you execute line 92? You get the value of x star that I plugged in, and then the endpoints of your 95% prediction interval, which you can easily read off. Okay. So just to wrap up, let's actually interpret one of these right here in the context of a specific histogram. All right. So if we look at what we're reading in this row right here, it's the 95th row. It corresponds to x95 from this bootpred object up here, and it's telling us that the 2.5 and 97.5th bounds of the prediction interval are these numbers right here, 1215 to 1718. Okay, so let's actually look at a histogram of that bootpred column right there. Let's look at bootpred. Bootpred $x95, and that histogram looks like this over here. And let's go back and make sure that that makes sense. So it's telling us that 1215, yeah, that looks about right, about 2.5% over there. And 1718, that also looks about right. There's 1718 about right there, and that also looks to be about 2.5%. Okay, so that's giving you some intuition for what these rows are telling you, and you could do the same thing for any row. You could go back up to row 63 and find the corresponding histogram for x63 right here. That would correspond to your prediction sampling distribution here for a value of daily circulation of 750,000. Those numbers right there, the 2.5 and 97.5th percentiles. Okay, so that wraps this up. And just to kind of remind you of what we've done here, we formed bootstrap prediction intervals. In the simpler case, we've only got one value of x that we care about predicting for. But then we modified the code in a relatively straightforward way to make predictions for a whole bunch of x's at once. Here, a whole sequence of possible daily circulations, starting very low and going up in increments of 10, 109 different predictions at once. And it didn't involve changing the code a little bit. Really, the tough part was what happened after and how to post-process and interpret the results that we get. And hopefully these kinds of functions that I've taught you here, using the apply function to do something for every column of a data frame, In this case, compute the standard deviation for every column of this bootpred data frame. And in this case, compute the 2.5 and 97.5 quantiles of that data frame. Will allow you to do that post-processing a little bit more efficiently, to do things like get the bounds of your confidence intervals and view those bounds right next to the values of x star that they correspond to.